All right, let's talk about the division theorem. So we're going to look at theorem 2.6 in the book. That is on page, where's my mouse? Da-da-da. Example. Division theorem. This is on page 17. And so this is going to be a theorem that kind of feels like duh, especially as we're getting started with here's what division means. Here's like all these different properties. That's kind of where we have to start. Of this feels super obvious, but we have to um, make it explicit. So the theorem states that for any two integers, a and b, where b is not 0, again, we don't want to break math, we're going to say there exists. Sometimes when I'm handwriting notes, I like to use the backwards E as a shorthand for that. So there exists a unique pair of integers, and the pair is Q and R. We're going to put a restriction on R, which is that R is greater than or equal to 0, and it is less than the absolute value of B, such that, sometimes you'll see in proofs that such that gets abbreviated ST. So such that A is equal to Q times B, or previously we've seen it B times Q. Again, commutativity, the order doesn't matter for multiplication, plus R. So that seems super long and complicated. Here's what it's actually talking about. Let's take number A is equal to 20 and B is equal to 6. If we do 20 divided by 6, again, I can't do mental math. So 3 times. So 6 goes into 20 3 times, remainder 2. And this is what we are doing here. And so this, we write this in a way that satisfies this equation in our theorem, which is just 20 is equal to 3 times, or that's why they wrote it the other way, 3 times 6 plus 2. 3 times 6 is 18, add 2, we get 20. So this is our A, this is our B, this is our Q, this is our R. And so what this theorem is actually saying is if these two numbers don't evenly divide each other, we need some notation for what the remainder is. We need to be able to say what's the remainder. So Q is still the quotient, so that's 3. That's the quotient. And then we have the remainder, and that's plus R. So if it doesn't go evenly, then it's plus R. If it does go evenly, then that's where we have the case of R could equal 0, because let's say if A is 18, 18 divided by 6 is 3, remainder 0, and that's perfectly fine. So this theorem is basically just saying, here's what the remainder is, here's how we write that in an equation. And we have this restriction because it doesn't make sense for the remainder to be a negative number, and we don't want it to be bigger than the number that we're dividing by, right? We don't want to, it doesn't make sense to divide something by 6 and have a remainder of 7, because that doesn't make sense. Then we didn't divide all the way. Okay, so let's do find the numbers. So let's say if that's A and that's B, what are Q and what is R? So if A, so we saw that for A is 20, B is 6, Q is 3, and R is 2. What about negative 20 and 6? Turn to your neighbor, try and figure it out. Right, so we have a restriction on R, no restriction on Q, other than it's got to be an integer.
Okay, so you're so 24. You're still 2. This is definitely I've never divided it in. Yeah, I should move it this way. I need like a cat maybe explain simple division step by step. I guess the remainder just has to be 2 because yeah. Hey, yes, there's 2 missing numbers. 0, 0. Yeah, yeah. Wait, that's how R can't be a negative number. This is malicious. Especially come back to it.
Okay, take 2 more minutes. Okay, shout out the numbers. What for negative 20 and 6? What are the Q? What's Q? Negative 4. What's R? 4. And for 20 and negative 6, what's Q? What's R? For 0 and 7, what's Q? What's R? Hooray! Yeah, so the important thing, especially as you look at these three, the important thing is that R can't be zero. R cannot be less than 0. So even though, like, we can't just make, like, we have to make it work and have R be a non-negative number. So that's the important part. All right, great job. So some terminology time. So remember that when we have, so we used to have just A equals B times Q, and now we have A equals B times Q plus R with restrictions on R. Remember Q is the quotient. So that's if we do long division. So if we have A divided by B, this is the quotient, remainder R. So that's kind of when we do long division, that's where all the numbers end up. So Q is the quotient, R is the remainder. And then we get into some terminology. So the book says we can write A div B to say that, or A div B equals Q. I don't know that I necessarily like that. I rarely see that notation. I think B divides A being equivalent to A is equal to B times Q is a lot cleaner. But this notation is there if we need it. The one that you do see and that you will continue to see is A mod B equals R. If you've taken a programming class, then you'll also see like A mod B. And we pronounce that percent operator, which is the modulus operator. It's the same thing as saying A mod B, right? And so, yeah, and so the remainder is so this is equal to A mod B. So if we divide 20 by 6, we get remainder 2. So 20 mod 6 is 2. Negative 20 mod 6 is 4. 20 mod negative 6 is 2. 0 mod 7 is 0. So yeah, so that's where we get that. Let's practice with this because modulus is one of those things that I find really cool. It's I kind of see it as like a clock where our time, if we're using 12-hour time, is mod 12, right? And so we've got two of these in the day. So we can have an 11:23 a.m. and also an 11:23 p.m. And we just add that extra unit to say which half of the day are we in. So let's practice. And so let's write the numbers 0 through 20 in, I'll do mod 3 for you, and then you can write mod 4, mod 5, and maybe mod 6 if you get there. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'll go up to maybe 11 or 12. And so for mod 3, we divide 3 by 1 or no. No, we divide. Wait, hold on. I want to do 1. Yeah, 1 by 3. You're correct. So 1 mod 3 and 3 goes into it 0 times. The quotient is 0. And our remainder is 1. If we divide 2 by 3, 3 goes into that 0 times. Quotient is 0. The remainder is 2. We divide 3 by 3. The quotient is 1. The remainder is 0. We divide 4 by 3. The quotient is 1. The remainder is 1. We divide 5 by 3. The quotient is 1. The remainder is 2. We divide 6 by 3. The quotient is 2. The remainder is 0. Are you seeing a pattern? Right, so this is where this is kind of why I like to think like it's like a clock where we hit 3 and we reset to 0. And so when we're computing mod 3, we're always counting how off by 3 are we? And so that's where we have the remainder restrictions, where it's 0 up until B, in this case, which is 3. So take a second and write down what these maybe, I don't know, maybe go up to 8 or so and see, like, I'm going to tell you the answer. It's 1, 2, 3, 0, but convince yourself that what all these numbers mod 4 is, what all these numbers mod 5 is. Okay, so I hope that's clear where mod 4 just counts 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And mod 5 goes up to 4. And so this is where the computer science perspective comes in handy, where we start counting at 0, and then 0 stands for all the multiples of that number. So what's 0 mod 3? 0. We divide 3 into 0 times with remainder 0. And so similarly for that. And what's 336 mod 6? 0. Why?
It's 0.
Exactly. 336 is a multiple of 6. Therefore, we've reset the clock and we're now at 0 again. Great. Okay, so some notes that the textbook has where it says that if B, the divisor, is greater than 0, then Q is equal to the floor of A over B, which makes sense, right? That's how we get the quotient. If it divides evenly, then we have no need for the quotient, or we have no need for the floor notation. If it doesn't, then we do need the floor. And then R is equal to A minus B to see how much off are we. And if B is less than 0, then we do that. So it says do it with the absolute value of B, and their way of putting it is Q is equal to the negative floor of negative A over B. So it's negating B and then giving it another negative sign on the outside in order to flip it back again. One thing they also note is that negative A divided by B and A divided by negative B are not necessarily equivalent. Okay, so we've got about 15 minutes. So I want to have some time for us to work on the examples. So we've got, this is the first day we've not run out of time to do the examples. Hooray. So we've got some examples over here. So I want us to focus on kind of two similar ones. So there's example 7, which is, this is on page 19, which is think of an integer between 41 and 59 inclusive, subtract 25 from that number and write down the resulting 2-digit number, then subtract 50 and square the result. And we're going to put those two numbers that we get right next to each other, and then prove that that big number is the square of our original number. So again, the answer is here in the textbook, but see if you can figure that out without referencing that. One of the things to think about, if I scroll back to what we did last time. So we had this 2-digit integer and the swap digits and then subtract the old number by the new number and then prove that that result is divisible by 9. And so it's all about thinking like, how do we write swap the 2 digits? How do we write a number in that form, like algebraically? So keep that in mind as we work on that. So the other example, let me see. So example 7, page 19. The other one you can work on is, I liked example 2 on page 17, which is it possible to pay an exact total of 100,674 when buying only $12 items and $32 items? So 1,674 with 12 and 32. And then example 7 on page 19, which is, that's the 41 to 59. It's in the textbook. So I'll write the 41 to
For example 7, what is tens maybe like
and
then you square it.
so okay, so 41. So let's say I want to pick 42. And then so I subtract 25. And I did this. No. I want to be over here. Minus 25 is 17. And then 42 minus 50 is -8. And you square that and you get 64. And so your resultant number is 1764. Okay, so work with your neighbors, try and solve example 7. If you get stuck, maybe switch to example 2. Go for it. All right, so it's 11:45. Thank you for coming. Homework 1 is due next class. I will collect it next class. Handwritten is fine. Next time we'll do matrices, so make sure to read 2.3 before we come to class, and that'll help us all be on the same page. Thank you. I will see you on Friday.